Let's start. Okay, we're good. Okay, so I guess as usual, let's have the reminder last time. And so last time we go over the properties of the LTI system by the four properties. So memoryless and invariability, causality, and stability. We went through describing them with this H function, this impulse response. Okay? Because we now know that every LTI system can be described by this impulse response H function, and then we can describe whether it has those four properties by just thinking about the property of this H function. So we see that if the system is memoryless, then that means that its impulse response must be some constant times the delta function. And LTI system is invertible, then this H function, then its impulse response. This is causality. Where is invertible? Okay, if it's invertible, then its impulse response must also be quote invertible in this way. So there must be an inverse of this impulse response, such that if you convolute this inverse of your H with your original H, then it go back to the delta function, which is the impulse response of the delta function is the impulse response of the identity channel. Okay, and we also see some nice functions. So we see that if we have a time-shifted delta function, so our impulse response, then our channel is a time-shifted. That the system is a time-shifted system. Okay, and then there is causality. So causality, we see that if a system is causal, then that means that its impulse response must be 0 for n or t less than 0. Okay. And finally, for stability is tricky, but the condition is here. The condition is that the system is stable if only if its impulse response is absolutely summable or absolutely integrable. Means that you sum over all its absolute value or integrate over all its absolute value, then it must be a finite number. If this is a finite number, then the system is stable. If only if this system is stable. Okay, those two need to be a finite number. And once again, stability is more confusing. So we need to remember that there are kind of two things to look for stability. So stability is defined on bounded input, bounded output, and so the system is this LTI system is described by this h of t, and we have input x and output y. And when we say bounded input, bounded output, we mean that we put a bounded x here, then the system is stable if every bounded x here give you bounded y. Okay, and then we also say there is another way we can look at this is you try to integrate this h of t. If it is absolutely integrable, then this system is also stable. Okay, but remember bounded and absolutely integrable are incomparable conditions, and so you want to check the integrate on h and check the boundedness on x and y. Okay, and so that's the full property, and we go a little more as unit state response, which is just a response to unit state function, this u of n or u of t. And then there is a variational support. So we see that if you convolute the function with another function, then the output function is a support just basically the two functions, basically the support of x plus the support of t. Support of x plus the support of h. Okay, so that's the support. So everyone okay with this? Okay, then today we are going to talk about a totally different topic. So we are going to talk about differential and the difference equation. Okay, and there are a few concepts. There is a concept of the conditional initial rates, and we are going to see that basically with the conditional initial rates, our solution, our differential or difference equation will describe a causal LTI system, and there are block diagrams. That's nice. Okay, so I guess a very short introduction. So why we like linear, these linear constant coefficient differential equations is because they describe a lot of things in nature. Okay, so like the example of system we give before, like the electric circuit or a car moving, then they are both described by those differential equations. So you can think about a lot of physics that describing nature will be will be a system that you can be written as a differential difference equation. Okay, and well, differential equation are a bit different from how we describe a system because it's an implicit simplification here. That means that so here you see this differential equation here. So this is just an example. Dy dt plus 2y of t equal to x of t. So well, this is an equation that relating y and x, and so you can put an x here, but you still need to solve something to give y. Okay, so the relationship between x and y here are implicit. It means that you need to do some solving here. Okay, and then they are even more tricky than this. Actually, this is not a full description of the system, as we'll see very soon. Okay, so here is a relationship between x and y, but even if you know x, there are going to be more than one y that satisfies this equation. Okay, and yeah, so we will need some auxiliary conditions to actually specify this system fully, such that you give x, and then this system will give you some y. Okay. Once again, remember a system is something that you put x as input, then you get some y as output. Okay, and yeah, so we'll need some auxiliary conditions, and some set of auxiliary conditions are initial conditions. But anyway, yeah, this is you need to put more restriction on this system, such that, or on these equations, such that you give x, you will get a unique y, like this arrow thing we usually give. Okay, and yeah. Okay, and so let's see this as an example. So let's go through this example, and we will learn a lot about solving differential equation. Okay, and so let's say we have a system described by this equation 2.95, and then we give it whatever input. So we have a very specific input here, x equal to k exponential function k e to the 3t u of t. So okay, so picture is here, x is like this. So it's u of t, so it's 0 when t is less than 0, and start at t equals 0, you have this k times e to the 3t function. So this is basically exponential growing function. We assume that k bigger than 0. Okay, so we have this exponential growing x of t like this, and we put it into this differential equation, dy dt equal to 2y of t equal to x of t, and we want to see what kind of y of t will satisfy this equation. Okay, and okay, so the first thing we see about this kind of equation is, and actually a very important concept, is that the solution to those two things together will be of this form. So it will be y of t equal to yp of t plus yh of t. Okay, and this is kind of tautology, but not. Okay, so this is very funny. So yp of t, this first thing, this yp of t is called a particular solution here. Okay, p for particular, and yp of t is a solution to here is actually 2.95 plus 2.96. Okay, so yeah. So yp of t is a solution. Okay, so it's 2.95 plus 2.96. Okay, and so you might look at this and you think, okay, this is done. You have a yp of t is a solution. Then why do you need also this yh part? Okay, And so this is a really funny thing is, well, I guess this go back to the thing we say here. So we say there are more than one solution to this input, okay? And to describe the more than one solution, we also have the homogeneous part, okay? So the thing is, you have if you just don't have x of t like the 2.96 here, if you have x of t equals 0 here, and then you can still solve 2.95. You can solve 2.95 for x of t equals 0. So if you write it down, it's this equation. dy dt plus 2y of t equals 0. And okay, so the solution of this is called a homogeneous solution. So homogeneous just means it's 0 here. Okay? And hopefully you can kind of see from linearity here that, so if you have just whatever particular solution here, and you add another homogeneous solution here, then because this left hand side here is very linear, so actually any particular solution plus any homogeneous solution is still a particular solution. Okay? So it's still the solution to this whole 2.95, because you kind of add yp plus yh here, and by linearity, then you get the yp part give you x of t, and the yh part give you 0, and you have x plus 0 still equal to x. Okay, and yeah, so this is the first important concept. This is a homogeneous solution. So a solution to this system by linear constant coefficient differential equation can also always be written as a particular solution plus a homogeneous solution. Any question so far? Everyone understand? Okay, kind of. And yeah, and also you see homogeneous solution. This homogeneous equation is nice because the solution to it is linear. So if you have a y being a solution to this equation, then you change y to say another constant y, so y to ay. Then you see that you put ay equals into this equation, you just get a times this equation, and this is 0, so it's 0. Okay, so yeah, so the solution to a homogeneous solution is always linear. Okay. But the solution to the whole thing, the particular solution, and sometimes it's not linear. We will not see an example, but I just say that. But we will see something related to this later. Okay, and yeah, so we have a particular solution and a homogeneous solution. And then our strategy to solve this equation is kind of guess the particular solution and guess the homogeneous solution. Okay, and okay, so let's start guessing the particular solution. Okay, so we want to solve those two equations together. So just this thing equal to this thing, dy dt plus 2y of t equal to k e to the 3t and the u of t. Okay. And let's focus on the t bigger than 0 part. Okay, so let's ignore this u of t. Let's just focus on t bigger than 0. Then x of t just is the exponential function, x of t equal to k3t. And then here we have a very ad hoc way of solving this. So it's basically because the x of t is a nice input function. So x is the exponential function, and we kind of just know or guess that the solution to this y of t here is also exponential function. Okay, actually it's an exponential function with the same coefficient here. So x of t is this k3t, and yeah, so we just say yp of t is some constant, another constant y to be determined times also this e to the 3t. Okay. And yeah, so we get this solution, and we just plug this into this equation back, and see whether we can solve for y that satisfy this equation. And of course our guess is correct, and we can solve for. So if we plug this 2.99 to the left hand side here, and then this x of t to the right hand side here, then here, so dy dt becomes, so y is still here, and then you have a ddt of this e to the 3t, so you get a 3 downstairs, so you get 3y e to the 3t, and so 2y is just 2 small y is just 2 big y times e to the 3t, And on the left hand side, on the right hand side, of course, you have this k e to the 3t. So you see our case is very nice because everything has a e to the 3t here. Okay? And so every term has a e to the 3t, so you can just cancel them out. And yeah, then you just left with phi y equal to k. So it's some constant equal to another constant. But y is some constant we want to determine, so phi y equal to k, then we just have y equal to k equal over phi. So we get a particular solution, we see that yp of t equal to k over phi e to the 3t. This is a particular solution, at least for t bigger than 0 part. Okay, and so everyone understand? Okay, we basically just take a guess. Okay, we see this exponential, and we take a guess, we get a particular solution. Okay, and then we want to solve for homogeneous solution. Okay, and the homogeneous solution is a solution to this thing with x being 0. Okay, but anyway, for homogeneous solution, we also just take a case. Okay, so we see that being well, this is not very good, but we just guess that we're having an exponential seems nice. So how about we just having another exponential? But now we don't have an input, so we don't really know what's the coefficient we should have on the exponential. So we just have another thing to determine. We have s here, so we just say yh of t is homogeneous solution is some constant a times whatever weird exponential e to the st. Okay. And once again we plug into the formula, and so we have dy dt. So a is everywhere, and the e to the st dt, then you get the s downstairs. So a s e to the st, then 2y, so 2a e to the st. So this is everything has e to the st, and with s plus 2, and we want this to be 0. Okay, and we want this to be 0, but e to the st should not be 0, and a is better not to be 0. Well, a is 0, then yh is trivial. Okay, so we want this always to be 0, then s must better be in the -2. Okay, so we see that we can have s equal to -2 and a equal to any constant. Okay, so a equal to any constant kind of satisfy what we expect. So we expect the homogeneous solution, the solution to homogeneous equation is linear. Okay, so it should be some whatever constant times your solution, it should be okay. Okay, so we have whatever constant a here times your solution. Okay, so yeah, so we have a times e to the, okay, so put everything back. So the full solution set is this particular solution, k over phi e to the 3t plus the homogeneous solution a e to the -2t. And the homogeneous solution will have to be determined constant multiplying it here. Okay. Any questions so far? Okay. Okay. Yeah. So this is for t bigger than 0, and this is really how much we can do for solving this equation 2.95 without extra condition. Okay. So we just have y of t equal to a to the -t 2t plus k over phi e to the 3t for t bigger than 0. Okay, and as we say in the beginning, so with just a differential equation and just the input, you cannot have a unique y. So y has a lot of freedom here. Okay, so you see here that we have a here that can be whatever. And also when t less than 0, we haven't solved for it. Okay, so we need to also kind of specify what happens when t less than 0. Okay, and anyway, so we will choose a way to have our auxiliary condition. Okay, so we need to put more restriction on our y plus y of t. Okay, and a good choice, actually the choice we'll make now and for a large part of the course, is this condition of initial rest. And this is kind of funny. So this thing is defined in a book, not this is actually not really defined in formal text. It's defined in this problem 1.5544. But anyway, so the condition of initial rest is like this. So it says that it's quite complicated. So it says that you have if you have an input x of t equals 0 for some t less than t0. Okay, so you think your x kind of starts somewhere. Okay, so there is some t0 that your x start having signal. Okay, so this is a very physical condition. Okay, so you think your x of t starts somewhere at t0. Then your y of t, you say then your y of t response must stay all 0 until you actually have x of t. Okay, so you think so this is the initial race condition. So if your x of t start at whatever time t0, means that it's 0 for all the t less than t0, then your y of t must also be 0 for all t less than t0. Maybe your y of t is 0 all the time, but anyway. For bigger than t0 is something, it should respond in some way, but for t less than t0, then there is no signal, then there is no response. So that's the condition of initial rest. Okay. Any question about this definition? This is a very important concept. Okay. Okay. So hopefully this is a kind of intuitive condition to you. Okay. So I think a good motivation for this is feels causal, and this is actually causal. So in problem 1.44, you can prove that if your system is linear and the initial rest, then your system is also linear and causal. And this is if only if. So if your system is linear and causal, your system is linear in the initial rest. Okay. And yeah, so you see, initial rest is a nice condition because it's kind of nice in two ways. So first way is nice is that this oftentimes give you causal, right? Because if your system is also linear, then your system is causal. Okay. And yeah, so initial rest gives you that the system is causal. And a lot of time we like our system to be causal. For example, at the start we say the differential equation might describe a circuit system or describe your moving car, and yeah, so a lot of physical process is causal, and so initial rest being causal is a very nice way to describe a lot of real world system. And okay, so it's causal, so it's intuitive. So and here you also kind of see it's causal. So your systems start have input at some time 0. Then you also only have one output starting at time 0. And okay, so it's give you causality. And another way is, well, it's also good for doing calculation as we just see. Okay, so this y being 0 for t less than t0 will give you, well, a lot of information about, well, you will already solve for all the y for t less than t0, and it will give you a lot of information about y is t equal to t0. Okay, and yeah, so this condition in this mathematical form will give us enough auxiliary conditions to solve our differential equation. Okay, and here we go over digression a little. Okay, so yeah, so for this chapter we'll focus on initial rest. But as you will see in some problems, and yeah, and later part of the course, I guess at the very end of the course, we will see that if you pick different auxiliary condition, then the system might not be causal, and sometimes it might not even be linear. Okay, so yeah, so it's not always linear. Yeah, as you can probably see here. So if you just say whatever initial condition, whatever auxiliary condition, then the input and output relationship might not even be linear. But as we'll see soon, with this initial rest condition, then this differential equation is actually causal in LTI, so it's very nice. And but for now, let's see the solution first. Okay, so let's back to solving this equation with initial rest. Okay, so initial rest, as we say, it tells us things at t0. So what happened at t0? Kind of think, I guess this is also a bit of assumption, so we assume y of t is continuous at t0. And so y of t is 0 at all t less than t0, and we're seeing y of t is also 0 at t0. Okay, so with the initial race, then y of 0 equal to 0. Because now t0, okay, remember our x of t look like this, right? X of t has a u of t here, and so it starts at t equal to 0. Okay? And so now our t0 is 0, and so y of t for t bigger than 0 is something, and for t less than 0 it should all be 0. And at t0 we also think is 0. So with the initial race, we think y of 0 equal to 0. And then finally we can solve for our a here. So we put t equal to 0 here, and y of t equals 0. So 0 equal to a plus k over 5. Because at t equals 0, the exponential are 1. Okay. So 0 equal to a plus 5. And yeah, so we can solve a equal to minus k over 5. Okay. And so for the t bigger than 0 part, we have our solution. Y of t equal to k over 5 is equal to 3t minus e to the minus 2t. Okay. And yeah, so this is e to the 3t part, and minus e to the minus 2t. Okay, so this is for t less than 0, sorry, t bigger than 0. And as we said, with the initial race, we also already automatically get y of t for t less than 0. It's just 0, okay? Because it's 0, just specified by initial race. Okay, so y of t equals 0 for t less than 0 by initial race. Okay, so we combine this thing and this thing, and the total result we want to write in one equation is y of t equal to k over 5 e to the 3t minus e to the 2t, and you just put the u of t here to cut off at t is equal to 0. Okay, and yeah, so that's how you solve the differential equation with initial race assumption. Okay, everyone understand? Okay, so yeah, let's recap very fast. So to solve a differential equation, so if we plug we put 2.95 and 2.96 together, we just get a differential equation with y. And to solve a differential equation, it usually has a particular solution plus a homogeneous solution. And the particular solution is just a solution to your differential equation, and the homogeneous solution is kind of arbitrary extra thing you can add to your equation. So homogeneous solution is a solution to this homogeneous equation. So you put the right hand side to 0, and you find out that because the solution to this homogeneous equation is linear, so you can put whatever constant a in front of it. And so your solution is always of this form a plus this arbitrary constant a times your homogeneous solution plus your particular solution. And then you can determine your arbitrary constant a by picking an auxiliary condition. And here we pick the initial race, meaning that your y of t start to have something until your x have something. Okay. And with this initial race condition, we solve for a, and also we solve for y of t for t less than t0. Okay. And we got our y of t. Okay. And here is another slide to give you some reminder of initial race. So the idea in initial race is that y of t is 0 until x of t is not 0. So there is some t0, that x of t will start having not 0, and the y of t will start responding. Okay. And yeah. And the tricky thing about this is initial race does not specify this 0 point at some fixed time. It has a 0 point. So this y of 0 equals 0. This 0 is related to your x of t, because the x of t has this u of t component. Okay, so the starting point is whatever starting point of the input. Okay, and also, as we will prove more general later, with this initial race condition, our system, well, this system is LTI and causal. Okay, so if we Okay, so it's kind of go backward. So we say we assume integral rates all the time, and then we try to put a different x over t here. So if we just assume integral rates and put a different x of t here, then the solution to this will be LTI and the cosine. Okay. Okay. Any questions so far? This is initial rest. This is an important concept of a large part of the course. Okay. If there's no question, then let's go to more. Well, this is we just finished an example of a particular differential equation, and let's go to a more abstract way to describe this differential equation. And actually, the differential equation we want to study is this linear constant coefficient differential equation. So there are two keywords here, or actually three. So we want to study equation of this form. So it's nth order linear constant coefficient differential equation. Okay, and it's of this form: summation k from 0 to n, some number ak, and dy d to the ky and dt to the k, dy dky and dt to the k. So you take the case derivative of y. Okay, and then similarly on the right hand side you have this linear combination of the derivative of x of t. So summation k from 0 to m and bk dkx and dt to the k. Okay, so you have differential of y to the kth power and the linear combination of them, and the differential of x to some kth power and the linear combination of them. I guess k is just some variable get summed over. Okay, and okay, so let's explain numbers. So there are three things we write here. So we say nth order. So nth order just means the differential on y is up to nth order. Okay, so for example, our favorite 2.95. Okay, this thing. So this is the first order differential equation, because the highest order of differential here is 1. Okay, so first order differential equation, and you kind of see there so big. So there is n here and m here, but n is more important because y is unknown. Okay, so m is kind of whatever. The nth order only depends on this n here, so the differential on y. Okay, so nth order differential equation on y, and there is linear. So linear is kind of obvious. It means that so the left hand side is a linear combination of differentials on y. Okay, okay, so it's just linear combination. So some with some coefficient ak, and in particular linear means that it's not quadratic, so you don't have x squared term or y squared term or like a y dy dt term. Okay, so it's so every order of different derivatives are separated, and they are combined by just this linear combination, and the same for the right hand side. So it's linear. And then finally, constant coefficient. Okay, so constant coefficient means that this AK and this BK here are constant. Okay, so it's not AK of t, it's not BK of t. They are just some number here. Okay, okay, so linear constant coefficient differential equation, and this is what we study a lot in this course. Okay, question on the definition. Okay. And okay, so then now we have not so important thing. So special case here is just n equal to 0. Then why did I? Okay, yeah. Special case n equal to 0. Then you can solve this explicitly. So if you have no differential here, then you just get it's a little annoying. Okay, so if you n equal to 0, then you don't have any derivative here, And so you just get a0 y equal to whatever x here, and you can put the a0 to other side, so you get just get y equal to this whatever thing you can calculate from x. Okay, because well, it's easy to calculate the derivatives, so you just calculate all the case order derivatives and adding it together, you get y of t. Okay, so that's just a special case. And more generally, we will see that the solution to this 2.109, so this linear constant coefficient differential equations, is similar to our example. So it will be a form of a particular solution plus homogeneous solution. Okay. And here we kind of assume we fix some x here. So with some fixed x. So with a fixed x, then we'll fix the particular solution with a fixed x of t. Yeah. I guess with a fixed x of t, then the right hand side just a function of t. But anyway. So with a fixed x of t, then the solution to our differential equation is once again you can write as a particular solution and homogeneous solution. And yeah, particular solution is a solution, but you can get the arbitrary coefficient times your homogeneous solution. And the homogeneous solution is once again solution to this homogeneous equation. So you have the same left hand side, so this linear combination of derivative of y, and but the right hand side becomes 0. Okay, and yeah, you can kind of check yourself that you have a solution to this plus a solution to this, then it's also a solution to this. Okay, because you add together, so everything linear. So you add together the left hand side, the right hand side is this thing plus 0 also equal to this thing. Okay, and yeah. And one more then, so solution to this homogeneous equation is called a natural response. And yeah, as we say, if a natural response, if you times the arbitrary constant to it, then it's also a solution. Okay, so y of t, the solution to y of t is a homogeneous solution. Then a y of t is also a. You have some constant a times y of t, then that's also a solution to, that's also a homogeneous solution. Okay, so yeah, that's your solution is particular solution plus homogeneous solution. And then a little slow. Anyway, do we have time? I think it's okay. Okay, and yeah, then finally let's go to this thing we have been talking about. We say we'll give a proof, then we give a proof. So we say linear constant coefficient differential equation, and now with our initial rest, and we are going to prove that the system as such is causal in LTI. Okay, and okay, so let's put all the conditions together. So first we have our nth order linear constant coefficient differential equation. So this is summation k from 0 to n, ak dky dtk equal to summation k from 0 to m, bk dkx dtk. Yeah, so this differential equation, linear differential equation, and we have our initial rest condition. And the initial rest means that your x of t starts at some t0, then your y of t also need to start at some t0. Okay. And with the initial rest, so we say that initial rest can be put into some nice numbers to solve for this. And actually, how we use initial rest is like this. Okay, so well, there are two parts. So obviously, for t less than t0, initial rest just told you that y of t equals 0. Okay, but for t equal to t0, then we say y of t. We kind of assume y is very smooth here, so we say y of t is 0, and it's actually a lot of 0 here. So we say y of t is 0 with up to n-1 order. Okay. And this is some funny thing here that is just a general thing for solving differential equation. So if you have an nth order, and this is why we would like to call it nth order differential equation. And so this n is very important here because kind of when n is larger, it's harder to solve. Okay. And in particular, we usually we have this kind of we know this kind of thing for solving differential equation. So if it's an nth order differential equation, then you need an auxiliary condition to specify it. Okay, to specify it down to a particular solution. And so that's why we have up to dn-1 dt n-1 here, because now we have basically n condition here. So from this k equal to 0 to k equal to n-1. So we have big N conditions here. So all those y of t and dy dt, d squared y dt. So all those derivatives are 0 at t0. Okay. And anyway, so that's the initial rates plus smoothness tell us. It tells us that y is a lot of 0 at t0. And then we claim that with these conditions and these equations, then now remember this is a system, so we can put different x here, and it will give different y. And this relationship between x and y is causal in the LTI system. Okay. Okay. Any question about the statement? Okay. And yeah. So this is a causal LTI system, and some digression before we go to proof. There's some explanation here first. So a lot of time you can solve this by how you solve the equation in our example 2.14. So basically you can guess some particular solution, and you can guess a lot of homogeneous solution, and you determine the coefficient to your homogeneous solutions by those equations. And okay, and I guess one thing extra is, so if your order, so it's bigger here, if it's larger, then you will get even more linear independent homogeneous solution here. So here we have a first, so in this example we have first order equation. That's why I only have a here to be determinant. But anyway, for n is larger, then you will have like n1 a2 to an, and that's why you need a lot of condition here. But we have more general tool to solve this in chapter 4 and chapter 5. Nice. And for now we have 7 minutes, so let's just complete our proof here. Oh, question? Huh? We are going to do the proof now. Okay. Yeah, so this is the proof. Okay. And I guess the causal is I guess we can see the causal part very first. So causal is actually very easy. No. So we need to prove it's LTI. So the LTI is harder, but if you prove it's LTI, then causal is very easy to see. Because if you know it's LTI, then you just try to calculate the impulse response h of t. So you put the input as delta of t, and then the output will be something. But we know that the system is initial rates, right? So you put delta of t inside, then the response must start at this t equals 0, right? And well, the response start at t equals 0 means that the response is 0 for t less than 0. And remember the review we just have a start of this today says that the system is causal if only if this impulse response is 0 for t less than 0. Okay, so yeah, so it's very immediate. So by initial rates and LTI, then you just calculate the impulse response. Then you see that the impulse response is 0 until you have an impulse. So the system is causal. Okay, and any other question? If not, then let's try to finish this with 5 minutes. Okay. And but before we do that argument, we need to prove the system is actually LTI. So we need to prove it's linear and time invariant. Okay. Okay. So linear, then we need to say that if we have some input out pair x1 go to y1 and x2 go to y2, then the linear combination, if the input is a linear combination of x1 and x2, then the output will be a linear combination, the same linear combination, right? So the output should be, actually alpha and beta. So input is alpha x1 plus beta x2, then the output should be alpha y1 plus alpha y2. Okay, and so our system is initialized, so we think we have some x1 starting at some t1, and you have some response starting at t1, and you have another input x2 starting at t2, and you have output y2 starting at t2. Okay, and now I think our input is some alpha x1 plus beta x2, and then we put in this that into this equation, and excuse me, and we see that, well, so we put this alpha x1 plus beta x2 into, it's very linear, so we can do linear things. So it's bk, then dtk, the alpha and the beta. So this thing is totally linear, so we can put this as just alpha and this term with x1 plus beta and this term with x2. This is just because, well, multiplication is linear and the differential is linear. Okay, and then this is a solution. Then because y1 is the solution to this differential equation, right? And so this is I should copy this, but anyway, so this is the left hand side of this equation, then that should be equal to, so this is the right hand side of this equation, so that should be equal to the left hand side, and similarly this is the right hand side should equal to the left hand side. Okay, so this should become this y thing, this summation y term, and this should become the summation y2 term, just because y1 and y2 is the solution to this equation. Okay, okay, so this is alpha and beta, and finally we see that so then we combine it back with linearity, so we see that this is a summation ak, so dk alpha y1 plus beta y2 dt to ak. So what do we see? We see that you put alpha y1 and so we see that if you put alpha y1 plus beta y2 on the left hand side, then that's the equation satisfying the right hand side being alpha x1 plus beta x2. Okay, so that's pretty nice. We see that it's kind of a spate of linearity. So alpha y1 plus beta y2 is the solution to the equation. And but we need to be a little more careful, and we also need to check that our solution satisfies initial rest. Okay, so alpha y1 plus beta y2 should have should be initial rest is respect to alpha x1 plus beta x2, and that should be good, because then we can check whether t1 is less than t2. So if t1 is a smaller one, then we see that alpha y1 and beta y2 must start at t1, and you see alpha x1 and beta x2 also start at t1. So you see that actually this satisfies initial rest. So this is very nice. So yeah, so we check the linear, and yeah, I guess for time invariant it's very quick. So for 5 seconds time invariant, you just do a change of variable, then you see that the system is time invariant, because whatever x of t has a solution y of t, then x of t minus t1 has a solution y of t minus t1. Okay. And let's complete the proof. I guess we'll do this a little more carefully next time, but so yeah, that finishes the part today. And any question? Otherwise, we will see you on Friday with difference and equation and singularity functions. Okay. Okay, then see you on Friday.